When designing an embedded system interface, we need to decide the location of two boundaries: the boundary between hardware and software, and the boundary between analog and digital. The placement of these two boundaries is among the most important decisions we'll make in the design of the interface. The boundaries between hardware and software and between analog and digital are critical decisions in the design of our system. Think of the application. Our first decision is what part of the application goes in software and what part goes in hardware, whether that be analog or digital. Within the hardware part, we can further subdivide between digital operations and analog operations. Where we place these two boundaries will influence the performance, the cost, and the capability of our system. The hardware-software boundary is characterized by several properties. How complex is the algorithm that we need to perform? If it's very complex, we're more likely to want to put it in software. If it's simple, we may think about putting it in hardware. Flexibility. Are we going to change it very often? The more frequently we want to change it or adapt it, the more likely it's going to end up in software. CPU utilization. Do we have enough CPU horsepower in order to be able to put it inside software, or do we have to rely upon hardware? Sample rate. The higher the sample rate, the harder the software and the processor have to work, and we may have to use hardware for very high rate processing. The numerical precision. It's easier, for example, to do floating point arithmetic using the processor and software than it is to build a floating point unit ourselves. Latency. How long do we have to perform the computation? For very low latency operations, we may need to use hardware. The interface requires a digital interface to the bus and a software driver on the CPU. This object diagram in UML shows us the structure of the system, and we can see from here the flow from input through buffers into the task, through output buffers, and back up to the output routine. But that flow becomes even more apparent when we look at a sequence diagram. We have an input which is placed by the interrupt service routine into a buffer. The task then reads that buffer, performs an operation, puts the result in another buffer, and that's then transferred to the interface using the output interrupt service routine. This simple state diagram shows us the sequence of operations that we need to do in a typical interface. We want to check the status of the system, we want to manipulate data, and then we want to update the status so that the software knows what's going on. Digital hardware connects the core of the interface to the bus and to the processor. Device drivers are software units that talk to that interface and transfer data between the interface and the tasks. This block diagram gives us the basic structure of the interface. We have registers for status, such as ready and done. We have data registers, such as character, and we have some control signals, such as ENC and ACK, which we often use in handshakes. We use state machines to control the operation of the interface. For example, a simple state machine will wait until some work needs to be done. We'll then perform the operation, perform a handshake, decide it's done, and then go back to the idle state. This table gives us the state encoding, or the binary representation of these states. These routines describe part of the software side of the system. The char string function manages the buffer that stores intermediate data. The char driver function talks to the interface itself using the peek and poke functions. This sequence diagram shows the flow of data between the character string buffer, the driver, and the actual interface. The analog to digital boundary is defined in part by the signal characteristics. Are we talking about high voltages or small voltages? The dynamic range of the signal, that is the ratio between the lowest and the highest signal, is very important. Temperature sensitivity plays a role in some systems. Analog circuits are more sensitive to variations in temperature. Digital circuits show less variation. Power consumption is an important characteristic for a lot of embedded systems. We need to make sure that we don't draw too much power and overload the power supply. Cost is a critical parameter in all sorts of system designs, and cost will help determine how we approach the problem. Latency, once again, is particularly important for reactive systems. How long does it take from when we see the input to when we deliver the output? Analog can provide very low latency in certain circumstances. To summarize, data in the embedded system flows from analog to digital hardware, then through the bus into the processor, where it's executed on by software. The data can then return back to the real world through the chain of digital and analog processing. Considerations of cost, performance, and flexibility help us determine where to put the boundaries between hardware and software and between digital and analog.